Swayam Prabha. Digital India. Educated India.
Welcome to this session of our lecture. So, it is basically if you remember whatever we have done in the last class. In the last class, we were looking into the eigenvalues and eigenfunctions of the form of the equation d square y dx square plus lambda y is equal to 0. So, we have already seen what will be the form of eigenvalues and eigenfunctions if we have both boundaries the Dirichlet boundary condition. Now, if we change the boundary condition at x is equal to 0 by a Neumann boundary condition, then we have also seen how the form of the boundary eigenvalues and eigenfunctions will take. Now, in this third problem we have taken up that we have changed the boundary condition from one of the boundary condition from Dirichlet to a Robin mixed boundary condition, and we are looking into the eigenvalues and eigenfunctions for this particular case. And we have already seen that the lambda cannot be 0. If lambda is equal to 0, then we are going to get a trivial solution. If lambda cannot be negative, if lambda is negative, then again we are also going to get a trivial solution. So, therefore, the only option that is left is lambda is positive and lambda is equal to alpha square. So, you will be having d square y dx square plus alpha square y is equal to 0. Now, we have already seen that the form of the equation will be e to the power m x. So, you will be getting m square plus alpha square is equal to 0, and you will be getting m 1 to as plus minus I alpha. So, the solution of this equation is a combination of the periodic functions, sine functions and cosine functions. So, y is equal to C 1 sin alpha x plus C 2 cosine alpha x is the solution to this problem. Now, we apply the both the boundary conditions to evaluate the constants C 1 and C 2. So, if we do that, the first boundary condition is at x is equal to 0, y is equal to 0. So, what we get is that 0 is equal to C 1 sin 0 plus C 2 cos 0. So, sin 0 is 0, cos 0 is 1. So, therefore, we will be getting here C 2 is equal to 0. So, what is the solution? The solution is of course, y is equal to 0 is equal to C 1 sin alpha x. So, C 1 sin alpha x is the solution. Now, let us utilize the other boundary condition and see what information we can extract for corresponding to the to evaluate the value of alpha. So, if you look into if you remember the other boundary condition at x is equal to 1, dy dx plus beta y is equal to 0. So, we evaluate dy dx from here. So, dy dx is nothing but C 1 alpha cosine alpha x and y is C 1 sin alpha x. Now, we put these things we evaluate these quantities at x is equal to 1 and put it here. So, dy dx is C 1 alpha cosine alpha x evaluated at x is equal to 1 plus beta times y is C 1 sin alpha x evaluated at x is equal to 1 is equal to 0. So, C 1 alpha cos alpha plus beta C 1 sin alpha is equal to 0. So, we get this equation from using this boundary condition and see what we get. We just take C 1 common. If we can take C1 common, it will be alpha cosine alpha plus beta sin alpha is equal to 0. So, you divide both side by cosine alpha, we will be getting alpha plus beta tan alpha is equal to 0. Now, there are two options again in this case to satisfy this equation. First one is C1 is equal to 0 or the quantity in the bracket is equal to 0, alpha plus beta tan alpha is equal to 0. Now, if C1 is equal to 0, again we are going to get a trivial solution, because the solution, if you remember, it is in the form of y is equal to C1 sin alpha x. So, therefore, C1 cannot be is equal to 0, because if C1 is equal to 0, we are going to get a trivial solution. So, what is the option now left? Beta tan alpha minus plus alpha is equal to 0. Now, again this is a transcendental equation. There are n number of roots of tan alpha is equal to minus alpha n by beta. So, this is known as a transcendental equation. Now, unlike the previous two cases, we had explicit solution for alpha n, but in this case we will not be getting an explicit solution of our alpha n, we will be getting a transcendental equation in this form. Now, again this equation tan alpha is equal to minus alpha by beta will be having n number of roots depending on the value of beta. So, depending on the value of beta, it will be having n number of roots, and we will be and this value, the index n runs from 1, 2, 3 up to infinity. And since we are not getting an explicit solution of alpha n from this equation, unlike the previous two cases, this equation has to be solved numerically. So, this is known as a transcendental equation, it is not explicit equation. So, it is implicit equation, not explicit solution. So, we have to solve this equation numerically in order to or iterative scheme. We have to take any iterative scheme. For solution of this equation tan alpha n is equal to minus alpha n by beta, we can talk about a Newton-Raphson algorithm. And solve this equation. Now, if you put different values of beta, typically these roots, these will be having the solutions of alpha n will be in the they will be increasing, there will be almost arithmetic progression with a common difference of about 3. The nature of this equation is such that this alpha n will be having they are almost in arithmetic progression with a common difference about 3. So, there is a trick to solve this equation by using Newton-Raphson technique. The trick is that you take, depending on the value of beta, we have to put the value of beta, and then you have to give a guess value of alpha. So, once we know the beta is nothing but a system parameter, knowing the value of beta, we give a guess value of alpha. The first root will be converging, that will be giving you the value of alpha. The next, you give a guess which will be nothing but the earlier solution plus 3. So, with that guess you will be getting the next root of this transcendental equation, and once you do that, then you give the third guess as the solution of the second loop, second eigenvalue, and then plus 3, the common difference is plus 3. So, the whole numerical algorithm will be put into two loops. The internal loop will be the Newton-Raphson rule loop for a known value of beta. The outer loop will be consisting of three values of will be consisting of the guess value which will be given in the increment of alpha. So, if we look into the structure of numerical solution, the structure will be there will be two loops, I is equal to 1 to let us say 10. This will be computing the 10 eigenvalues. Do j is equal to 1 to 10. So, first loop will be Newton-Raphson for solution of this. So, it will be we just finish it off here. Then whatever the solution you are going to get, this lambda guess will be nothing but lambda solution of the earlier case plus 3. So, that ends the outer loop. So, this will be the inner loop, this will be the outer loop, and at the end you are going to get all the solutions eigenvalues lambda 1, lambda 2 up to lambda alpha 1, alpha 2 up to alpha 10. So, that is how one can compute the eigenvalues of this transcendental equation. So, what are the corresponding? So, we cannot get the explicit expression of the eigenvalues in this particular case. So, we write down this transcendental equation in order to designate this eigenvalue alpha n divided by beta is equal to 0. So, we say alpha n is the solution, is the nth solution to this equation. This is also known as nth 0 to this equation. So, these are the eigenvalues, nth eigen. So, alpha n is the nth eigenvalue, which is nothing but the nth solution to this equation. And what are the corresponding eigenfunctions? The corresponding eigenfunctions will be C1 sin alpha n x. So, nth eigenfunctions is Cn y n is equal to C1 sin alpha n x. Now, let us summarize what we did. We looked into the solution to this, we looked into the non-trivial solution to the equation d square y dx square plus lambda y is equal to 0, and we used the following boundary conditions and see what are the eigenvalues we got and what are the eigenfunctions we got. So, these are the boundary conditions and these are the eigenvalues and these are the eigenfunctions. So, boundary condition, the first boundary condition is that at x is equal to 0, y is equal to 0, at x is equal to 1, y is equal to 0. So, with this we got the eigenvalues as n pi and the corresponding eigenfunctions are sine functions sin n pi x. If we had the boundary condition at x is equal to 0, a Neumann 1, so it becomes dy dx is equal to 0 and at x is equal to 1, y is equal to 0, we have 2n minus 1 pi by 2 as the eigenvalues and cosine functions as eigenfunctions. And on the other hand, the last one, if we have the boundary condition at x is equal to 0, y is equal to 0, but at x equal to 1, we have a Robin mixed boundary condition dy dx plus beta y is equal to 0, then we have a transcendental equation which is the solution of this transcendental equation becomes eigenvalues. So, beta tan alpha n plus alpha n is equal to 0. So, eigenvalues are roots of this equation or zeros of this equation and the corresponding eigen functions are sin alpha n x. So, if you see, if we just change the boundary conditions, the eigenvalues and eigenfunctions change. If we have a Dirichlet boundary conditions on both the boundaries, the eigenvalues are n pi and eigenfunctions are sine functions. If we have a Neumann boundary condition at x is equal to 0 and Dirichlet boundary condition at x is equal to 1, we have 2 n minus 1 pi by 2 as the eigenvalues and cosine functions as eigenfunctions. Similarly, if you have a Dirichlet boundary condition at x is equal to 0 and a Robin mixed boundary condition at x is equal to 1, we will be having a transcendental equation, roots of whose are the solutions or the eigenvalues of the problem and sine functions are the eigenfunctions. So, we have seen that by selection of different boundary conditions, one can get into we can land up into the different eigenvalues and eigenfunctions. In most of the chemical engineering applications, these are the boundary conditions we are dealing with and these are the eigenvalues, and depending on the boundary conditions and situations, one can land up with different eigenvalues and different eigenfunctions. Okay. So, next we will be looking into some of the special ordinary differential equations. Which are in the for which the eigenvalues and eigenfunctions will be defined. The first case we have taken, there is not a special one, that is in Cartesian coordinate d square y dx square plus lambda y is equal to 0. We have already taken care of this equation, this we have already done. Next special ordinary differential equation we will be looking is this form 1 minus x square d square y dx square minus 2 x dy dx plus n into n plus 1 into y is equal to 0. The boundary conditions are at x is equal to 0, y is equal to 0, at x is equal to 1, x is equal to plus 1, y equal to 0, x equal to minus 1, y is also equal to 0. So, this will be x equal to plus 1, this is equal to x equal to minus 1. So, this is basically at x is equal to plus minus 1. Now, again if you see that the differential equation is homogeneous, there is no non-homogeneity term is present there, the boundary conditions are also homogeneous. So, therefore, this will be giving a this will be a candidate, this set of this system including the differential equation and the boundary conditions is a candidate to have an eigenvalue problem. So, the solution of this equation is in the form of C1 p n x plus C2 q n x, where p n is known as the Legendre polynomial and q n is known as the Legendre function. If so, we have already seen that if this is the form of in the first case, this is the form of differential equation, the sine function, cosine function, etc., the eigenfunctions, and we have already seen the eigenvalues. But if the form of the equation is a special equation like this is known as the Legendre equation. And this occurs mostly in spherical polar coordinate system. Then if this is the this is the differential equation with this homogeneous boundary conditions that at x equal to plus minus 1 it is equal to 0, then the solution will be constructed by combination of Legendre polynomial and Legendre function. Then we should know about some of the properties of this Legendre polynomial and Legendre functions. So, we list down some of the important properties of Legendre polynomial. This one are first one is P n of 1 is 1. So, that is the first property. Second one will be minus 1 to plus 1 P n square x dx will be 2 divided by 2 n plus 1, and third one will be minus 1 to plus 1, that is the domain of x, P n x times P m x is equal to 0 for m not equal to n, where m n are integers. So, this is also known as the orthogonal property. If you remember the inner product as we have defined earlier, for two matrices we have for two vectors we have found out the inner product between the two vectors will be equal to 0, and in case of continuous domain, in case of continuous function, inner product is nothing by it will be replaced by an integration. So, integration of P n x multiplied by P m x dx will be equal to 0. So, therefore, this is also known as the orthogonality condition. Now, let us look into the some of the property of Legendre function. So, these are the most important properties which we will be utilizing quite often whenever we will be talking about a Legendre equation as our governing equation. For Legendre function, the property is that at x equal to plus minus 1, q n is unbounded. That means, q n tends to infinity or it will be infinite in nature. So, that is the property of Legendre function, that is at x equal to plus minus 1, q n is unbounded. Now, typically we will be dealing with the Legendre functions, Legendre polynomial and Legendre equation whenever we are working on in spherical polar coordinate. We will be landing with the Legendre equation. Now, some of the properties, some more properties, that P 0 x is equal to 1, P 1 x is equal to x, P 2 x is equal to half 3 x square minus 1, P 3 x is half 5 x cube minus 3 x, P n cosine theta is 1, P 1 cosine theta is cosine theta, P 2 cosine theta is 1 by 4 3 cos 2 theta plus 1, P 3 cos theta is 1 over 8 5 cos 3 theta plus 3 cos theta. So, this is P 0, this cannot be P n. So, P 0 cosine theta. So, these are the in polar coordinate. So, we just replace x is equal to cosine theta. So, we will be getting P 0 cosine theta is 1, P 1 x by cosine theta is cosine theta, P 2 cosine theta is equal to half 3 cos square theta minus 1, that is given by 3 cos 2 theta plus 1, and similarly we will be getting P 3 cosine theta. So, in spherical polar coordinate you will be getting the Legendre equation as your governing equation, and the solution will be constituted by Legendre function and Legendre polynomial. We have discussed some of the properties of Legendre polynomial. A Legendre function, the major property is that it goes unbounded at the two boundaries x equal to plus minus 1. Next, we talk about a particular form of or the special form of ordinary differential equation, that is a Bessel equation. And this equation will be in common whenever we are talking about the solution in cylindrical polar coordinate. Whenever we are working in cylindrical polar coordinate system, we are landing up with the Bessel equation. So, the Bessel equation is in the form x square d square y dx square plus x dy dx plus x square y is equal to 0. So, the solution of this equation is in the form of y of x is equal to C 1 j 0 x plus C 2 y 0 x. For a general equation, this is known as 0th order Bessel equation. General equation means it is alphath order of Bessel equation, and the equation is in the form of x square d square y dx square plus x dy dx plus x square minus alpha square times y is equal to 0, where alpha is an integer. So, just check, if we put alpha is equal to 0, we are going to get back this equation, the 0th order Bessel equation. For alpha is equal to 1, for any value of alpha, you will be getting, this is the Bessel equation. For alpha is equal to 1, the last term will be x square minus 1. So, the solution of this equation is in the form of y x is equal to C 1 j alpha x plus C 2 y alpha x. So, you can replace alpha by n. So, you will be getting nth order Bessel equation. So, nth order Bessel equation is nothing but x square d square y dx square plus x dy dx plus x square minus n square y is equal to 0, n being an integer. Again, the solution is composed of j n and y n. So, C 1 j n x plus C 2 y n x. So, we will be having j n as the Bessel function of first kind of order n, and y n is the Bessel function of second kind of order n. So, now these will be quite common whenever we will be talking about the cylindrical polar coordinate system. The solution will be composed of Bessel functions first kind and second kind, and then let us look into some of the important properties of Bessel functions which you should know, and they are very important and they will be useful whenever we will be solving this type of equations. So, properties of Bessel equations, Bessel functions. Most important property is that y alpha x or y n x, the Bessel function of second kind of order n, is unbounded at x is equal to 0. That means, at x is equal to 0, y n x goes to infinity irrespective of any value of n. Second important is that j 0 and j n for any n 0 to 0 1 2 3 is they are bounded at x is equal to 0. That is quite important. The third one is that j n oscillates about x axis. So, that means, this is very important property, like the sine functions and cosine functions or the trigonometric functions like sine function, cosine function, tan function. They in fact, tan function they do not oscillate, but the sine function and cosine functions they oscillate about the x axis. Similarly, j n oscillates about x axis. So, if we plot j n x as a function of x, it oscillates about x axis with diminishing amplitude. That is important. So, therefore, j n x will cross the x axis at several points, and all these points are the roots of the equation or the eigenvalues of the corresponding problem. So, we can easily evaluate. So, basically this property of the Bessel function makes them that there are infinite number of roots are possible of this equation j n x is equal to 0. For this equation there are infinite number of roots are possible, and all of these roots are corresponding, they correspond to the eigenvalues of the problem. Okay. So, we will come to that later on, but let us look into the properties of j n, and now let us consider the another variation of Bessel function or Bessel equation. consider another form of Bessel equation. The equation becomes x square d square y dx square plus x dy dx minus x square y is equal to 0. So, if this is the form of equation, then the solution is in this form, y is equal to C 1 I 0 x plus C 2 k 0 x. Now, for a general form x square d square y dx square plus x dy dx minus x square plus alpha square times y is equal to 0. Let us say x square plus n square to make it more uniform. Now, this equation is known as the modified Bessel equation. This is the modified Bessel equation of 0th order. This is modified Bessel equation of nth order. So, therefore, the will be getting the solution for this particular problem as y function of x is nothing but C 1 I alpha x I n x plus C 2 k n x. So, the idea the difference between the Bessel equation and modified Bessel equation is that there will be minus sign and it will be plus, and in case of Bessel equation the solution is constituted by j 0, j n and y n functions. In case of modified Bessel equation the solution is composed of I n and k n functions. Both appear in the solution of if we work in the cylindrical polar coordinate system. Now, I n is known as the modified Bessel function of first kind of order n, and k n is modified Bessel function of second kind of order n. K n, the important property is k n is unbounded at x equal to 0 and I n they are bounded at x is equal to 0. Now, these there are recursive formulas are available for j n and I n, and these equations the various relations of Bessel functions, modified Bessel functions are available in any standard textbook of mathematical functions. You can look into the book of Kreyszig. And look into the properties of Bessel functions and modified Bessel functions of different orders. Their recursive formulas are available to connect them up. The differential of Bessel function, the differential of modified Bessel function, all are available in any standard textbook of mathematics of the first year level. Next special ordinary differential equation that we will be talking about is Euler's equation. The Euler's equations is in the form of x square d square y dx square plus a x dy dx plus by is equal to 0. Now, the form of the solution is in the form as y is equal to x to the power r. This is the form of solution. If we put it that, then what is dy dx? Dy dx is nothing but r x to the power r minus 1. One more differentiation. So, d square y dx square is nothing but r into r minus 1 x to the power r minus 2. So, if we put it here in the governing equation, x square r minus 1 x to the power r minus 2 plus a x dy dx is r x to the power r minus 1 plus b y is x to the power r is equal to 0. So, what you will be getting is that you can in everywhere the x containing term appears to be x to the power r. So, this becomes r into r minus 1 plus a r plus b multiplied by x to the power r is equal to 0. So, the characteristic equation we get is r square minus r plus a r plus b is equal to 0. It is a quadratic in R. So, therefore, there are two roots are existing, each root will be corresponding to each solution. Okay. So, if you solve this equation, we will be getting r square minus r plus a r plus b is equal to 0. So, you will be getting r square minus r into 1 minus a plus b is equal to 0. So, you will be getting it is a quadratic to two solutions r 1 2 is equal to minus b plus minus under root b square minus 4 b divided by 2. Okay. So, one root corresponds to plus, another root corresponds to minus. So, therefore, the solution of Euler's equation is that y is function of x c 1 x to the power r 1 plus c 2 x to the power r 2, where r 1 2 is given by the in terms of the known parameters a, b, etc. So, these are three forms of special functions. These are the four forms of special ordinary differential equations we have talked about. First one we talked about d square y dx square. So, these are basically the Cartesian coordinate. D square y dx square plus lambda y is equal to 0. So, we have discussed different boundary conditions and the form of the eigenvalues and eigenfunctions in detail. Then we talked about the differential equation in spherical coordinate. This is given by the Legendre functions. Next, we talked about the cylindrical coordinate. So, these are the Legendre equation. and the solution is composed of Legendre function and the Legendre polynomial. And third one, we talked about the cylindrical coordinate system, the governing equation that you will be getting the Bessel equations. These are the ordinary Bessel equations and modified Bessel equations, and the solution will be composed of Bessel functions and modified Bessel functions of first kind and second kind. And the fourth one, we just looked into the Euler's equation, as we will be seeing later on in this course that Euler's equation will be useful whenever we will be talking about a spherical coordinate system. It will be constituting a part of the particular solution. Okay. So, these are the special ordinary differential equations the chemical engineering students and chemical engineers, they quite often come across in various chemical engineering processes. So, these are the, whenever we are talking about the flow through a channel, we are talking about the rectangular coordinate or Cartesian coordinate. Whenever we are talking about the discussing about the flow through a pipe, so or some kind of flow through a tube, then we will be talking about the cylindrical polar coordinate system, where the governing equations will be given by the Bessel equations. Whenever we will be talking about a spherical coordinate system, for example, you would like to store a gas in a spherical container and you would like to find out the heat transfer characteristic, mass transfer characteristic, or a spherical ball, you would like to find out the heat transfer characteristic. Okay. So, they will be quite often they will be utilized in the different applications like metallurgical applications. Then we will be talking about the spherical polar coordinate system, and the Legendre functions or Legendre equations becomes very important, and they will play a big role in solving those equations. And Euler's equations also play a role whenever we will be discussing the problem in a spherical polar coordinate system. So, these geometries, these coordinate system and geometries are quite common in chemical engineering applications, and we have already seen what are the different governing equations will appear to characterize such systems. Next, we will just talk about the adjoint operator, that is quite important whenever we are solving a chemical engineering system in continuous domain. So, we start with adjoint operator. Now, if you in any chemical engineering system can be expressed in a mathematical form, in this form LU is equal to F, or LU is equal to 0. This is for a generalized non-homogeneous system, and this is for a homogeneous system. Now, where L is the operator, okay. Now, this operator will be the differential operator. It may be del t minus del square del x square. Okay. So, this is a typical operator to characterize an unsteady state system. L can be only a gradient operator del square. So, it will be del square del x square plus del square del y square plus del square del z square in a 3-dimensional process. So, this is typically an operator for a steady state system. Now, if you look into the matrix operation, I will just bring a corollary of matrix operation. A x is equal to b in a discrete domain. This is the matrix so what is the solution to this system? X is the solution, a solution vector, A is the matrix, B is the non-homogeneous vector or coefficient vector. So, the solution is given as x is equal to A inverse B. So, we have to find out A inverse, matrix inverse, in order to get the solution vector. Similarly, in case of the chemical in continuous domain, LU is equal to F. So, U is the solution, L is the operator, F is the non-homogeneous term. So, what is the solution? The solution is obtained by L inverse F. Now, this L inverse in most of the cases are can be identically used for adjoint. So, in order to get these adjoint operator, if L is the operator, we find out L inverse as adjoint operator. So, in order to find out a solution U, you have to determine the adjoint operator, so that you will be getting the complete solution. So, evaluation of adjoint operator is very important, and for in the continuous domain, and once you will be evaluating the adjoint operator, you will be in a position to get the complete solution of the chemical engineering system. So, I will stop the class at this point, and in the next class I will just take up and derive the general formulation of how to get an adjoint operator given an operator for different boundary conditions as well. Then we will look into the various theorems of eigenvalues and eigenfunctions, which will be quite important for the further development of our system and the processes and solution of various chemical engineering equations. Thank you very much.